All right, so today I'm going to talk about some joint work with Larry, and it's, so the title is The Sierpinski Carpet as a Final Coalgebra Obtained by Completing an Initial Algebra. So this is kind of an extension of some work he did with about the Sierpinski gasket, which is triangles. So we're going to look at the Sierpinski carpet, which is squares, in an effort to sort of generalize this work. So we'll talk about kind of where it is now and where I hope it can head. So to start out, let's talk about what we mean by algebras and coalgebras, and I'll give some motivating examples of what these are about, and then we will talk about some of the work that's been done with like the Sierpinski gasket with the triangles, and then talk about the work we did with the square. So, okay. All right, so let's start by defining algebras and coalgebras. So we'll start with a category C and a functor, an endofunctor from C to itself. So it just maps objects to objects and morphisms accordingly. We say that an F algebra is an object in the category along with a morphism from the category from FA to A. Okay. And then what we're interested in particular in is initial F algebras. So it's kind of exactly what you would expect. It's that they can all map into other F algebras. So specifically, we say that big A with its map little a is an initial F algebra. If for any other F algebra, like this B with its morphism little b, there's a unique morphism which takes A to B so that this diagram commutes. So it kind of preserves the algebra structure. And that it's unique. This is going to be important. So, and these initial algebras are kind of a way for us to capture some information in different ways, which we'll talk about in an example in a moment. So this is one of the structures or like constructs we're going to be interested in. And then as well as the dual notion, which is going to be a little better suited to our purposes at the end, which is a coalgebra. So it's exactly the same thing with everything reversed. So an F coalgebra is going to be, again, an object in your category, and then a morphism from the category that goes from A to FA. And we say that an F coalgebra is a final F coalgebra if any other F coalgebra can map into it in this analogous way, so that this diagram down here at the bottom commutes. Also, can you guys see the cursor when I point at stuff? Is that visible? Mm-hmm. Yes?
Yeah.
Okay. All right.
Yep.
Okay, good. All right. So yeah, so let me give some examples of some sort of like information we can capture with these. And ultimately what we're going to do, as the title would indicate, is that we're going to view the Sierpinski gasket as one of these final coalgebras. So we'll talk more about what that means specifically. But let's, yeah, so let's give some motivating examples over why these algebras are like a nice way to see what's going on. So we're going to work in this example in the category of sets. And then we're going to find a set functor, which takes it takes a set to 1 plus a set x to 1 plus x. So it's just going to add some new fresh element that's not already in x, and it'll map. So in the category of sets, the morphisms are just set maps. So it'll take a set map and then take the new guy to the new guy. So that's how this will act on this category. And then so we're going to look in particular at the set of the natural numbers. So that's an object in the category of sets. And this morphism going from n plus 1 to n, where that new element that gets added by doing the plus 1 is going to go to 0. And then all the elements of n will just go to n plus 1. So this is obviously a set map. So it's a morphism in the category. And so far we have an algebra because we have our object and we have our map. And then what we're going to do is we're going to show this as an initial algebra, but actually it's going to be such in a really useful way. So let's talk about recursion. So recursion on n, we can view this in the following way. If you have a set A, big A, and then you have a little element a, or little a in A, and a function from F to A, then there's a unique way to map the natural numbers into A so that this phi of 0 is this designated element, this little a, and then phi of n plus 1 is f of phi of n for all n. So being able to do this uniquely is going to coincide exactly with what it's going to mean for this algebra that we just defined to be an initial algebra for this functor. So another way to think of that is that given given an algebra, big A with a morphism from A plus 1 to A. So let's talk about that for a second. So this is going to capture this information here because whatever alpha takes your fresh element to is going to be your designated sort of first element there. And then the rest of A, the rest of it restricted to just A is just going to be your map F from A to A. So this recursion on N gives you this unique map from N to A, which makes this thing commute. And this thing commuting is exactly what we've sort of described up here. And you can check that sort of for the different elements. Okay, so this is meant to be just sort of a motivating example of like the kind of relevant information to other things that we could capture by identifying these algebras as initial algebras. So that's, okay, is that, yeah. All right, so I also want to talk about coalgebras and final coalgebras. So let me give a slightly different example for that. And we'll see this is sort of more like continuous in nature, and these are going to be the right thing for us to consider fractals. So let me start with a different object here. So this is going to be the natural numbers with an infinity element. Okay, so that's going to be the object we start with. And then we'll define a morphism from n to n plus 1. So this is the same functor on sets f to take 0 to the fresh element, to take x plus 1 down to x, and then to take infinity to infinity. And I use star to denote the fresh element. Okay, so far we have a coalgebra because we have our object and we have our morphism from the category, which goes from the object to its image under the functor. Okay, and then so let's look at any other coalgebra and look at the information that gives us. So let's just take A to be an object with a morphism from A to A plus 1. So in other words, another coalgebra. And we can view this as giving streams of elements in A in the following way. So if you start with some x in A, you can just consider the stream that you get by applying this little a to it however many times you can. So this may terminate if after some number of applications of the morphism, you get to this star element, because then you can't apply a to it again because it's not defined on A plus 1, it's just defined on A. So you may get some finite stream, it may terminate after some finite number of steps, or it may give you an infinite stream if you never like land on that star element via this little a map. Okay, so right, so this we can view this coalgebra as sort of giving this information, and then this one I gave at the top, it turns out, is a final coalgebra, and here's how you can view that: is that there's a unique way to sort of capture this. So here's how we're going to do it. So we're going to define f from a to n that we're going to need to be in that diagram that's going to have to commute. And it's going to be uniquely determined as follows. So if x is the start of some infinite stream, we're just going to have f of x be infinity. And then in this case, f plus 1 of a of x will also be infinity because a of x will still be the start of an infinite stream. And then f plus 1 on that will just be f because it's not the special element. Okay. And then otherwise, if x is the start of a stream with some finite length n, then we'll let f of x be n. Okay, so then you can see what f plus 1 is going to do. So f plus 1 of a of x will just be f of a of x as long as n plus 1 is still natural number. And then when you get down to that last element, so the last thing that goes to the star that tells you that your thing terminates, then f plus 1 will of course take that to the star. Okay, so it turns out this is in fact going to be exactly the unique morphism that makes this diagram commute. And again, you can sort of like toy around with particular elements and make sure this makes sense. Like if you take x in A, which gives you like some infinite stream, then you should check that a of x is still going to go to a thing that gives you an infinite stream. So f plus 1 of that, like we noted up here, is going to go to infinity. And similarly, if you go this direction around. Okay, so like I mentioned, this is sort of more continuous in nature. But these things are good ways to like capture relevant information from other places. So this is what we have in mind when we are working towards viewing these different fractal sets as ultimately coalgebras of an appropriately chosen category and functor. Okay, so let me start off with some results that are some early results. So this is Freuds theorem, and this is about what we call bipointed sets. So we're gonna take the category of bipointed sets, and ultimately we're gonna work in metric spaces, but let's just start with sets for now. These are going to be sets where you have some underlying set X, and then you have two identified points. So you have, we use the top and the perp or bottom. So you can just think of them as the top and the bottom. So intuitively, you should be thinking of like the unit interval with 0 and 1 as the bottom and the top. Okay, so this is going to be, we'll take the category of these guys, and then here's what the functor that we're going to define. Now, the intuition around like choosing our functor correctly is that a way you may want to think about it is like picking your functor so that it kind of describes iterations of the fractal that you're working up to. Okay, so for this one, this isn't like a super geometrically or visually at least interesting thing, but it's a really nice example because it kind of gives us this framework to think of this functor in the right way. So what we're going to do is we're going to let M be L and R, which is going to stand for left and right, excuse me, for a bipointed set X. And then we're going to let M tensor X be just the pairs of elements of M and X modulo this equivalence right here. So what you can think of is that you have a left copy of X and a right copy of X. And then what we're doing is we're matching up the top of the left with the bottom of the right. So we're identifying those points. Okay, and then to view this as a new bipointed set, we need to pick a bottom and a top. So the bottom in the new guy is just going to be the bottom of the left, and then the top of the new guy is going to be the top of the right. So you just take two copies of your thing and tack them together in the middle, and then you take the bottom and the top to be the bottom of the bottom one and the top of the top one. Okay, so here's the cool thing. So if we let, so like I said, sort of intuitively, you should be thinking about the unit interval. And then we can define, so we'll define a map I of X to take X in the unit interval into the left side and then multiply it by 2 if X is less than or equal to 1/2. And then onto the right side and do 1 minus 2X if X is on the top half, if X is greater than 1/2. Okay, so you're sort of taking your unit interval and just mapping it into 2 copies of the unit interval that are scaled down. So the point is that this I, the unit interval with this map, this little I, turns out to be a final coalgebra for this functor. And I want to talk about a proof of this, not the original one, but here's how we can think about this. And we're going to kind of use this idea throughout. So this is going to be really important. So to see that this is a final coalgebra, one way that we can approach this is by saying, okay, take any other coalgebra, and what we need is a unique morphism that makes this diagram commute. Okay, so what we're going to do is define a map on the set of morphisms from X to I. Okay, so it's going to take a morphism F and map it to this I inverse and this M tensor F and this E. So that's going to be another morphism from X to I. Okay, so this little I needs to be an isomorphism, which this one is. Okay, so we're going to take this map and then note that this the set of morphisms from X to I we can view as a complete metric space, and in particular, this phi is going to be a contractive map, so it's going to have a unique fixed point. And the fixed point of this is going to be exactly the thing that will make this guy commute, and it's unique, which is what we need to see that this thing is in fact a final coalgebra. Okay, so that's kind of a technique that we're going to see again. So I want to give it in the context of this one in particular. Okay, so then moving forward from this, sort of a nice next step is to consider tripointed metric spaces. So this is going to be the framework under which we can consider something like the Sierpinski, gasket, like the triangles, right? So and notice metric came into it. So this is going to be kind of a nice addition to the information that we capture, because it's natural to want to consider these geometric objects in the metric spaces in which they live. So we do want to, in fact, capture that information. Okay, so in order to think about this Sierpinski gasket or Sierpinski triangles, our category now is going to be tripointed sets. So these are going to be sets with distinguished elements for top, left, and right. So again, you can think about the corners of a triangle. And we designate that they're pairwise 1 apart. And then our objects need to be metric spaces, which are bounded by 1. Okay, and then our morphisms in this category are going to be short maps, which are just non-increasing maps, which preserve these designated points. Okay, so with that category in mind, some examples are, well, here's some iterations of the Sierpinski triangle, okay, where obviously the top, left, and right are just these corners here, or something like the set of just top, left, and right alone. That's going to be an initial object, because obviously there are top, left, and right points in every object in the category, and a map that takes those to those will be, in fact, isometric, because we have this requirement that they stay exactly pairwise 1 apart from each other. There's no final object in this category, so there's no object that everything maps into, and you can see this just by thinking of something like, if you suppose there is a final object and then take top, left, and right with like some middle point that is 1 away from all of them, there won't be a unique way to map that into a final object. You might be able to map it more than 1 way. So, okay, so, all right. Okay, so we need to define the functor on this thing, like we did with bipointed sets, which kind of corresponds to iterations of this fractal. So what we're gonna do is let this M, again, you wanna think of M as kind of like an index set telling you where to put copies of X. So this M is going to be ABC, so that's gonna still be top, left, right. Okay, and then we'll define a functor, M tensor X, which again, it's the analogous thing. So it's gonna be pairs of indices from M and then elements of X. And then we have the following equivalents. So for the top copy, the left corner is going to be identified with the top of the bottom left copy. So in other words, if this is the A copy, you're saying identify this point with the top of this copy, etc. So that's saying sort of where to stick these things together. And I'm going to mention this more times going forward, but one way you can sort of conceptualize this is to think about that is kind of like taking copies of an object in your category, scaling them, which we'll talk more about in a moment, and then gluing them together at these points that are being identified via this equivalence relation. So, okay, and then you can think of this new object as a tripointed set by identifying the top with the top, the left with the left, and the right with the right. Okay, so those are going to be tripointed sets, but we need to define a metric on this thing. So here's how we're going to do it. So we're going to use the quotient metric. So here's how it's going to work. The idea is that, like I said, you can kind of think of like gluing scaled copies of your original object X. So what we're going to do, we're going to scale them by 1/2. Okay, so in our new object, in our M tensor X, if you have 2 points that live in the same copy or have the same first index, their distance will just be half of what their distance would have been in X. And then otherwise, what we want to do for points that are maybe in different copies is that we want to take the inf of the score. So what is the score? It's the like if you take a finite path through this thing, and then like take all the distances for segments on your path, but as soon as you use an identified points, those are going to have distance 0. Okay, so the point is that it gives you a way to kind of walk around this and take points in different copies, and then you have to like walk through these identified points to get between. Okay, so right off the bat, this quotient metric so far is a pseudometric because it's an inf of lengths of these paths, yeah. But turns out that there is this there's a way to sort of explicitly give the what these distances, or give explicit expressions of what these distances are going to be for all the cases. So you can get this to be a metric, or show that this is a metric in this way. Okay, so right, so that gives us a functor on the category of tripointed metric spaces. Okay, so here's some of the sort of a summary of what we know about this, and this is work of Larry et al. Put them up here. Okay, so here's what we know, and I want to put this slide up because it's going to be kind of a roadmap of how we're going to approach thinking about the square. So first of all, okay, so if we start with this initial object, this with just the top left and right, and then look at this chain of applying M to it. So this, we've got this inclusion map here, and this is this unique morphism we get from this thing being an initial object, and then take this initial chain. These guys are isometric embeddings, and you can think about why that makes sense even just in the first application, right? Because you're taking stuff to itself. So you can take a colimit of this chain, and it's going to be this union, sort of disjoint union modulo the images of these maps. And this thing is also going to be preserved by this functor. So M tensor G will be isomorphic to G. Okay, so once you've done that, you can apply Adomic's theorem, which I'm going to state in detail in a little while because we're also going to use it. But basically, using this information, we can get that if you take such an isomorphism between M tensor G and G, you can get this thing to be an initial algebra for this functor. Okay. And then here's the technique they use that we're also going to use, which is to then take the Cauchy completion of this G that comes from the initial algebra and flip the direction of this isomorphism. And that thing is going to turn out to be a final coalgebra, and this uses an argument similar to the one we saw for Freuds theorem. Okay. And then the thing you get at the end, you can show is by Lipschitz equivalent to the Sierpinski gasket, like in the plane. So so that's what we mean by like obtaining the fractal as a final coalgebra. We're going to find a final coalgebra, which is a metric space, which is by Lipschitz equivalent to this, like the fractal that we're interested in. So these are kind of the steps we're going to take, but there's going to be a few departures from the approach here. So I will point those out as we go along. Okay, so here's the biggest difference. I'm going to put up these pictures. Yeah, okay. All right, so I mentioned that you can kind of think of applications of this functor as like gluing copies of these things to each other at some identified points. So one of the biggest differences between thinking about the triangles versus the squares is the kind of stuff you're gluing on. Okay, so I put up some iterations of the triangle here, and you can sort of see how I like take this first one, scale it down by half, take 3 copies, and then glue them together at these 3 corner points. And then you can do that again. So scale this guy down and then glue at these corners, etc. Okay, so that's sort of a useful way to think about it. And it's reflected in the information that's preserved by morphisms and that's identified in the category that you have these like top, left, right corners that need to behave a certain way. So here comes the issue with a fractal like the Sierpinski gasket, which is this thing where you take a square and cut it into 9 squares and like remove the middle and then do that with the remaining 8 squares over and over, is that if you want to think of it in terms of this gluing, it happens along segments. It doesn't happen at points. So if you think of like taking this first square and you shrink it down by a third, and then you want to glue 8 copies of it together, what you're doing is you're like, if you take this top left copy, you're identifying its whole bottom side with the top side of this like middle left copy, etc. So there's a lot more information to sort of keep track of, sort of describe this gluing in a useful way. So that's sort of a major departure from like the work done here. So I guess I was interested in this question because I was thinking like, how can this generalize? And one of the things that needed to happen was like managing gluing on different kinds of sets other than just like some finite number of points. Okay, so here's how we're gonna do it. All right, so here's the category we're going to work in. It's going to be the category of square metric spaces. So already our identified set we want to think of via a function. So this M0 is going to be the boundary of the unit square, which I just wrote like this. And so we say an object is a square set if it has an injective map, which identifies this boundary of the unit square with points in X, okay? And then we say that X, along with this identification of this boundary, is a square metric space if it's a metric space bounded by 2, which we'll talk about why we're using 2 in a little bit, and such that our like SX satisfies some conditions. So what we want for the boundary is that we need distances along a single side to coincide with the unit interval. Okay, so notice we're not having the whole boundary just behave exactly like the unit square and like on the plane, for example. So we just need a few of these sort of features though. We need along a single side to act like the unit interval, okay? And then we need points on opposite sides to be at least 1 apart, and we need corners to not collapse. So what I mean by that is if you look at 2 points with a corner between them, so 2 points on adjacent sides, we want their distance to be greater than or equal to the distance from each of those to that corner. So the idea is that your corners aren't like crushing down, that they're sort of held out by some lower bound. Okay, so these are sort of analogous to like the requirement for the triangles that your corners be pairwise 1 apart. These are just the conditions we need to make this sort of gluing behave correctly. Okay, so that's those are going to be our objects in our category. Okay, and then so some examples of some square metric spaces. Well, this just this boundary of the unit interval all on its own with the identity as you're identifying the edges. And in fact, this is obviously an initial object. There's a unique way to map it into all the M0s, preserving it. It's just the this SX. Okay. Or another example is this is the whole unit square where S is the inclusion map with what we call the max metric. And this is something we're going to use a few times. And this is just the metric where you take the max of like the horizontal component and the vertical component of your like distance between your points. So it'd be like if you have like x0, y0 and x1, y1, it'd be the max of like the difference of x0 and x1 and y0 and y1. Okay, so that's going to be a useful thing. All right, and then the morphisms are just going to be short maps, again, non-increasing maps, which preserve the boundary. So they take Sx of Rs to Sy of Rs, if you're going from X to Y. Okay, so that's the category we're going to work in. So this is all structure that we need to maintain. So throughout, like as we're defining our functor, we need to make sure this stuff is satisfied. Okay. So here's how we're going to define our functor. So remember I said M is like an index set. It's like telling you where to put stuff. So we need an 8-element index set to designate the 8 squares. We're going to put copies of X in. Okay, so it's just the 0, 1, 2, but we want to leave out 1, 1 because we want to omit the middle. Okay, and then we can define, so this is like a little more explicit description of how we're going to get our quotient metric. So we can define D on just M cross X. So we haven't modded out by any equivalence yet, but just this D on pairs from M and X to be scaled by a third if you're in the same copy and to just be the max otherwise. And then this is what we're going to use to define our quotient metric in a second. Okay, so so from here, we need to mod out by identified sides. So here's how that's going to look. Or here's a picture of how it looks. So all the sides that are identified are given by these little squigglies I put in here. Okay, so the quotient metric is what you do is you take, like if you want to find the distance between 2 points, it's the same thing. You take paths between those points, and then on your path, if you have identified points that are identified by this equivalence relation, so like points on these sides that match up, then that has distance 0, and otherwise you use the distance from the previous slide. So you take the inf over all of those, okay? And then ultimately we need to view this as a square metric space. So for the sides, we just do this in the obvious way. Like if you want the left side, you scale these all down by a third, and take the side. Okay, so yeah, so let's talk about this quotient metric. So like I mentioned with the triangles, just how it's defined, it's a pseudometric because they're imps of distances. So you could have distinct things go down to 0. So we need to figure out how to get that to not be the case. So here's how we show it. Now I'm going to put up the statement of this theorem. It's really wordy, but most of it you get for free. So let me just put it up here and I'll talk about what's going on. So like I just said, the metric we just described is a pseudometric. So, okay, here's how we get it to be a metric. Now, when I wrote this, I wanted it to be in some reasonably general context. So I didn't want to give a proposition that only worked for square metric spaces. So I have us working in just any category of metric spaces which are bounded by some n with an initial object so that you get this structure. So obviously this is motivated by the square metric spaces, but it also applies to the previous examples we've seen, right? If your M0 is just top, left, right, then your injective map is just identifying the points. So we need that image to be compact, which for square metric spaces it is. The morphisms need to be short maps, preserve the structure. And then we have our index set M that we're going to define our functor with, and our equivalence relation, which one thing to note is that the equivalence only depends on M. It doesn't depend on X, okay? So it only depends on the index set and like this identified set. Okay, then consider the quotient metric, and then we have a few other sort of technical things. We want it to be isometric and closed. This happens for free when you're working with M0 being finite, but in this case, these are easy to check. Okay, and then you have to have a way to define the new boundary on your new object. But then the last requirement that we're going to need is that the shortest path between points in the same copy of X is in fact their distance in X. So in other words, you can't like travel outside of a copy and then back to get a shorter path than if you were just stayed inside your copy. So we're going to talk more. I put it in blue because that's the like sticking point. The rest of these you kind of get for free. Okay, so the punchline of this is that then the quotient metric, the distance in the quotient metric is actually witnessed by a particular path. So it's not just an inf, you get an actual path that whose score is the distance. So in fact, it is a metric because you have an actual path. So it can't just drop down to 0 for distinct points. Okay, so like I said, this thing about the shortest path between points in the same copy of X being actually just their distance in X, their scaled distance in X, I guess, is the part that's going to take some work to check. Okay, so we're going to talk about that in this context. Okay. Oh yeah, and just this note that all these requirements are pretty readily satisfied except for the blue one. Okay, so let's talk about how to show that for square metric spaces. So here's how we're going to do the shortest path between elements in the same copy of X is their distance in X. So here's how we show it. So we're going to use the region contact graph. So what is this graph? This is like saying which copies of X have shared points. So let me just go back a couple of slides for a second. Like you can see that here, right? So like 0, 0 and 0, 1 share like this whole segment, or even 0, 1 and 1, 0 share a point, right, for that corner. So that's all captured by this graph, okay? And then the idea is that if you think of paths that can be used to determine the quotient metric, if you start with 2 points in the same copy of X, that's going to correspond to a cycle in this graph, all these paths, right? So the way this works is that you examine the, you just go by cases and look at the possible cycles in this graph and show that for any such cycle that the score you're going to get is bigger than the distance you would just get between the points in the original copy. Okay, so yeah, so I do have some questions about how we could maybe rephrase this requirement in terms of a property of this graph, sort of, or if there's a way to, because again, we have this sort of broader goal of kind of generalizing this to more fractals than just these square ones. So I'd be interested in that. I'm also interested in what other fractals this can apply to, and even if there's maybe like a geometric requirement we could put on our boundary shape, like maybe it's a concavity thing that would capture this correctly. So those are some questions I'd be interested in thinking about. Okay, but regardless, this is true for our square metric spaces. So that's that works. Okay. So yeah, so let's start talking about some M algebras. Oh yeah, so this thing's going to be a functor because we get our quotient metric is in fact a metric, preserves the sides, it does all the stuff we have to do. So yeah, so this guy's a functor. Okay, so let's start talking about some algebras, and I wanted to just give this example because I'm going to use it in a little bit. So to give some like kind of geometric intuition for what's going on here. Okay, so let's let U0 be the unit square with the max metric. That's the one we talked about the components. Okay, and then alpha 0 is going to be defined like this. So you're in M tensor U0, it's an index from M and an element of the unit square. And so we're just going to take them to a third of their sum. And this exactly maps it how you would expect. So like if you viewed M, so this is M tensor U0. If you viewed that in the plane, it's going to take it to like where it would go in the plane. Okay. And so then this map, you can then hit with M to view it between higher iterations of this. So like if you want to go from M squared tensor U0 to M tensor U0, it would be M tensor alpha 0. Okay, so you get these maps that go this direction. So these are going to be algebras because they go from like the functor of an object to the object. Okay, and here's the sort of sticky thing that we have to pay attention to kind of throughout is that these are, oh, right, so that's what I just said about how you can get bigger ones. Okay, so these are, they're injective and that you can check, and you can check that M preserves injectivity. But most importantly, they're short maps, which is something we need to be careful of because the morphisms in our category have to be short maps. And the intuition for why this works here is that in higher copy or higher, like more applications of M, you get more holes, right? So if you take the starting unit square, it's solid and you can just take any path through you want. But as you start applying M, you have holes that you have to walk around that you can't cut through. So like an obvious example of this is like if you go from like 1/2 0 to 1/2 1 in U0, well, if you go to M tensor U0, you have to go around that middle hole. Okay, so the point is the distances get longer as you apply M more often. So the maps going down are going to be short maps. Okay, so that's the idea. And like I said, we're going to use this in a little bit. So okay, so that's an example of some M tensor algebras. Okay. All right, so what was the next step in the roadmap that we saw for the gasket? It was to take a colimit of a chain that looked like this. Okay, so remember I said about the triangle that you had this chain of the initial object and then applying M to it. And then you had some colimit of that, which came kind of in a nice way because this was a chain of isometric embeddings. So it turns out here's one sort of place in this context which differs is that these are not isometric embeddings anymore. Okay, so and the geometric intuition for this is that if you start with just the boundary and not a solid square, in fact, this picture totally still works. If you think it's just the boundary, then each application of M is going to add more grid lines. So you could possibly get a shorter distance by like walking along one of these lines. So an example here would be if you go like 1/3 0 to 1/3 1, in here you have to go around the outside, but then once you apply M, you can just go along this line. So those distances go down when you only have the boundary that you're starting in. Okay, so these are short maps, but they're not isometric embeddings. So it actually requires some work to get the colimit to be a metric space. And I put in progress up here because there's more general results coming, but I'm just going to talk about this in the context of these square metric spaces in particular. So here's how we're going to get that. So we take the colimit in the same way we take this sort of disjoint union of these things, and you can kind of see how that would be. They kind of live inside each other. Okay, but the problem is, again, you want to define so, okay, right. So you take this union of these things, and what we can view G as like these finite addresses, like you have n applications of M and then like some element of your boundary. So you can kind of see how all these guys like live in this G, okay? And then you can define a metric on it where like you start with an object in G, which is some finite address, and then you can view that object in some Mn tensor M0, and then like keep applying these maps to that object, and then just take the inf of the distances between those. So like the distance in G is going to be the inf as you take distances like along this chain. So again, we're defining a distance with an inf. So it's a pseudo metric just with that definition. But here's how and this is why I put an extra layer on this chain here. Here's how we're going to see that this is in fact a metric. Is what we're going to do is look at these distances whose inf is the distance in G, and we're going to map them up to this top layer and then go all the way down to U0. And here's how it's going to work is that all these maps are injective, and U0 is a metric space. So if you take your two objects and they're distinct, and then you go up here and all the way over, you're going to get distinct things. So they're going to have a distance that's positive. And because these are short maps, it's going to be a lower bound for the distance over here. Okay, so, and in fact, it's going to be a uniform lower bound even as you move along this chain. So that's how you get that distinct objects in G are going to have positive distance. So this was a place where we had to do something kind of different than what went on in the triangle case. Okay, right, so this is going to be the object that we're going to use for our initial algebra. Now that we can sort of like, this is what we needed to get this thing as the colimit of this guy. So it is in fact colimit, it's a metric space. We also have to show that it's preserved by M, which it is. You can just show this directly. Okay, then now is where we get to apply Adomic's theorem, which is what was done in the triangle case, which is the following, that if you have this initial chain and you have a colimit and it's preserved by the functor, and you take this A to be this unique morphism that makes this thing commute. So these are just the things that give you this co-cone. Anyway, this technical requirement, then you get this thing to be an initial algebra. So that's what we're going to apply here to get our G to be an initial algebra. We just had to do a little more work to see that G was in fact the colimit of this chain. Okay, so that's good. So we have an initial algebra. So that was sort of one of the bullet points on my list of sort of stuff that happened to the triangle. Okay, so we're there. So then the next step that we need to do is take the Cauchy completion of this. So this is going to behave very similarly to what went on with a triangle. This generalizes, like you don't have to do anything really special. But here's how it works, is that we're going to start with our initial algebra. This guy's an isomorphism, so flip it around. And then we can take a functor which takes our objects to their Cauchy completions. This is in fact a functor on this category. It preserves the structure that we need. Okay, and so then you can show that there are these natural isomorphisms. So what are we doing with these? The point of this is that we want to see that this Cauchy completion functor commutes with M. So it takes a little bit of work to show that you have these natural isomorphisms that do this and invert each other, but it's reasonably routine. And the only special thing we had to do for square metric spaces is make sure that these things in fact preserve the boundary, which they do. So, okay, so you have those guys. So you can get this sort of, you can use these to find a map from the Cauchy completion of G to M tensor the Cauchy completion of G, because, right, so you just hit this eta inverse with that C, and then you use this natural isomorphism. Okay, so we'll let Q be that Cauchy completion, and then let mu be that map. So we get this thing. So this Q with this map is going to be a coalgebra. It's going in the right direction for that. Okay, and what we're going to show is that this thing is in fact a final coalgebra, and that this Q with its corresponding metric by taking the completion is going to be bi-Lipschitz equivalent to the Sierpinski carpet. Okay, so that's what's coming. Oh, yep, there. Okay. All right. So to show this as a final coalgebra, we're going to use the following theorem. Now, this is kind of a restatement of what was used in the triangle paper, and it's possibly more general. So if some questions around that, but here's how this is stated. So we call A a short enriched category if for some metric on the Hom sets, if you're given two morphisms, and H and G, which you can compose, that the distance you get after composing is bounded by the distance between the morphisms. So this follows from our category, like the category we're working in, that the morphisms are short maps. So we get this requirement for free in the context that we're working. And I'll talk more about that in a second. Okay, then here's the theorem that if you have a contracting endofunctor, which our M tensor is, and you can just show it directly, and then you have a coalgebra, then as long as the morphism of your coalgebra is invertible, and for every other coalgebra, this Hom set is non-empty and complete, then this thing is a final F coalgebra. So, okay, so that's what we're trying to show for mu and q. Yeah, okay. This stuff we mostly get for free. So we know that gamma is invertible. And the completeness of the Hom set, well, there's going to be a metric on the Hom set that we get with the suit metric for the morphisms. Okay, and that'll be complete because Q is complete. Okay, so the only thing we need to do to apply this to our circumstances, to square sets, square metric spaces, is show that this Hom set is non-empty. So that's going to be sort of the bulk of the work from here to the end. Okay, so we're going to do that, but let me just make sort of a note about this sort of short and rich requirement. So I thought this was kind of cool because the way the theorem is stated doesn't require that the objects of your category be metric spaces. It's only requiring that there's a way to put a metric on the morphisms, which satisfies some condition. So I'm wondering if like, it's not immediate that having this sort of short enriched requirement like induces like a metric on the objects themselves. Like if there's an object with a single point, then yeah, it will. But like our square metric spaces, for example, or even just square sets without a metric space, we don't have any objects with single point, right? So, or I guess another way to phrase this is, are there interesting examples of metric space or of categories which are short and rich, but whose objects are not metric spaces? Okay, so that's sort of something considering. Okay, all right, so like I said, our last big push now is to show, okay, all right, is to show that given another coalgebra, that there's a map from that B to the Q, that Cauchy completion of G that we defined. So here's how that's gonna work. There's a few sort of stages. So the first one is to show that Q is the limit of this chain. So this was the chain I put the picture up of, where U0 is the unit square, and then we take those short maps that go down from iterations of the unit square, okay? So this requires some work, but what does it mean to be the limit of the chain? Well, we have a cone, and then if you take any other object that has a cone, then there's going to be a morphism from that to Q, okay? So remember, our goal is to get some morphism from B to Q. So I suggestively put a B hat here, because what we're going to do is find an intermediate B hat, which we can map B to, and then make that B hat into a cone for this chain to get our morphism from B hat to Q. So that's how we're going to do this. Okay, so how do we do it? Well, given a coalgebra B with or beta, we can find B hat to be the colimit of this chain. Now, let me just say a little bit about that real quick. This looks familiar. This is like how we found G to be the colimit of that initial chain. But remember, for G, we had to do some like trickery using U0 to make sure G was in fact a metric space. So for our B hat, we don't have that luxury. We don't know that this maps into this in any obvious way. So what we're going to do is just mod out by distance zero stuff. So we'll just take the pseudometric and mod out to get a metric space. And then it'll take a little bit of work, but we can show that that is then going to be preserved by M. So we do want the colimit of this thing, but it's not just going to be so straightforward. Okay, which is fine. All right, so that's going to be our B hat. So here's the roadmap, is that there's definitely going to be a map from B to B hat, just via the cocone. And then this is the B hat that I want to show has a cone to this chain, which will give me a map from B hat to Q. So that's what we're going to do with this B hat. Okay, right, so we have B to B hat. Okay, and let me say one more thing. Why are we using B hat? Well, the reason that we're not trying to go directly from B to Q is that we really don't have any information about B. B is just some object that lives in a coalgebra. But besides that, we don't know anything about it. So trying to like just like from cold trying to define a map from B to Q is going to be hard. So what we're going to do is take advantage of this coalgebra structure to give us an object that we sort of know something about. And the sort of the point is that, remember, we were able to view G as kind of like these finite lists of indices from M. B hat's going to behave in a similar way. Okay, so that's what we're going to take advantage of. Okay, so here's how we're going to get our cone for B hat. So every element of B hat, we can really view them kind of as being associated with some infinite lists of elements from M. And the idea is that we can just take their images down this chain, okay? So when I described G, I said, you know, we have these finite addresses. The point though is that like if you land on some like, so it would be SB of RS, you can use the equivalences in the definition of like SM tensor B to like expand that thing. So like if your final thing on your list is 0, 0, you can just put a bunch of 0, 0s in there as arbitrarily long and it'll identify the same point. Okay, so you can get an infinite list by just walking down that chain. Okay, and so here's the function that we're going to define from B hat to U0. And so we're not going to Q yet, it's coming, but first we got to go from B hat to U0, and it's just going to be these sums of powers of 1/3 times the indices in that infinite list, okay? And again, you can sort of conceptualize that this is sort of like a geometric view of this thing. And the same, I mean, this should look familiar, right? This is a lot like that first alpha 0 map that we defined between copies of U0. Okay, so that's how we're gonna look at this. Okay, and then here's the point is that, okay, so this is a map from B hat to U0. Now we're trying to get to Q, so here's how we're gonna do it. Note that we said B hat was preserved by M tensor. So if I look at Mn tensor this F, that's a map from Mn tensor B hat to Mn tensor U0. But really, because Mn tensor B hat is isomorphic to B hat, I can view this as a map from B hat to Mn tensor U0. So what was all that? What did we just do? This is a cone. So this is going to give us a cone from B hat to that chain. Okay, so that's what we needed to take advantage of Q being a limit to get our map from B hat to Q. And I put unique in parentheses. It is unique, but we're composing it with some other stuff. So that's not, it doesn't really matter. Okay, so yeah, the point was that we took advantage of this sort of, again, you can kind of think of it as like a way to geometrically place these sort of iterations in the plane. That maps us to U0. So that's going to get us this cone to that chain of U0s with holes cut out. And then because you have a cone to that chain and Q is a limit of that chain, you necessarily have a map from this B hat to Q, which is what we needed. So putting it all together, because we have B to B hat and B hat to Q, this Hom set is non-empty as required. So that was the blue thing in the theorem. So now by the theorem, this thing is going to be a final coalgebra in square metric spaces. Okay, so I think I have like 2 minutes left and I have like one more thing to say, which was that last punchline, which is that now that we have final coalgebra, it's by Lipschitz equivalent to the Sierpinski carpet in the plane. So here's how we're going to do it. So we take the Sierpinski carpet with the in the plane with the Euclidean metric. Now I notably never really defined this, but one way you can think about it is you can think of the transformation described by like taking 8 copies of this and pasting them, 8 copies of like unit square and pasting them in those 8 spaces and repeating that. And so you can think of this as the unique compact non-empty set that's preserved by that transformation. Okay, so that's what we wind up using. Okay, so then I'm going to define this map, which should look familiar. It's that same map. And it's going to go from Q to this C. And it turns out this is a bijection. So the way you show that is you just look at the image of this and show that that's compact and obviously it's non-empty and is preserved under that transformation. So that checks out. Okay, so here's the bijection between Q and C. And then by Lipschitz equivalence, well, we're gonna do an intermediate step by way of our max metric. So the max metric is by Lipschitz equivalent with the Euclidean metric. And it's just the triangle inequality. And squares. So that's easy to show algebraically. And then working with the max metric, it turns out we do get the bi-Lipschitz equivalence with Q. And the way this proof goes is that the reason I use the max metric is it's easier to think about just horizontal or vertical segments, which is how the max metric is calculated. So, so the way this works is that you're going to approximate dq with the distance in some mn tensor m0. Because remember, Q is the completion of G, which is like the disjoint union of those things. So you can approximate distances by looking in those and then examining horizontal or vertical segments in those sort of finite iterations, and like calculating how you have to walk around the holes, and then you get this bound. So that's going to give you the bi-Lipschitz equivalence. Okay, so I think I'm going to finish. Yeah, that was it. So thank you. It's 201 or 501. So yeah, that's